figures, because you'll see things like largest, smallest, maximum, minimum, things like that. That's the clue to tell you that you're dealing with optimization, all right? So applied maximum, minimum problems, all right? Big challenge with any word problem, or sometimes the biggest challenge, would be to come up with the equation that you have to do stuff to. In this case, find a derivative. But I find that in terms of the setup, these can be easier in some cases than related rates. In other cases, they can actually be trickier, but I find that more often than not, it's easier. All right, so you can read through the process, but I'm just basically going to walk through it anyway. Jack wants to create a rectangular garden. All right, so that's my clue to draw a good-looking rectangle. Has 100 feet of fencing to make the border. All right, sounds like a perimeter. What are the dimensions of the plot with the largest area that can be enclosed with this fence? All right, so talk about area. The largest area, dimensions that go along with that area. Now, there is no natural boundary here. It's just four sides. So you could rely on prior knowledge and avoid doing any calculus here. If it's a multiple choice question, that's fair game. If it's pre-response, different story. But the type of rectangle with the largest area would be a square. So 25 all around and call it a day. But if we have to show the work, then we have to do some calculus, right? If that's the case, then we can assume that the length and width are the same. So define one as x and the other as y. I have a relation here, and that is 2x plus 2y would be equal to 100. I can clean that up. X plus y equals 50. All right. So the thing that we want to maximize or find the largest value of would be the area. So this is an equation that's going to be useful for us, but the more important equation would be area, and area would be equal to length times width, in this case x times y. All right, so where possible, I want to avoid having a function of two variables. So I want to have it a function of one variable. So I could swap out an x or a y based on my perimeter model. All right, so I can conclude here that y is equal to 50 minus x. Or, what did I just hit? That's so weird. Y is equal to 50 minus x, or you could say x is equal to 50 minus y, either way. All right, but that allows you to make a substitution. And so our area could be represented as x times 50 minus x. For convenience, let me just make that red. For convenience, we would say 50x minus x squared. All right. If we're looking for the largest or smallest value, maximum, minimum value, it's implying that we're looking for extrema, or relative extrema specifically. Relative extrema comes from finding the critical values and then creating a sign chart. So that's what we want to do. Now, maybe you don't want to do the sign chart. Maybe you want to apply the second derivative test for extrema. That would be fine too. Either way, you need to justify that your critical value is in fact going to give you a max versus a min in some way. All right, so I'd find a prime. Let me go purple for those keeping score at home. 50 minus 2x. Set my derivative equal to 0. Solve for the value of x. That ends up being my critical value. All right, so your pathways here at this point are really threefold. One, common knowledge. I'll say common sense, but I'll say common knowledge as a more PC version of that. The common knowledge would be this is a downward facing parabola, the negative leading coefficient. If that's the case, then any extreme value would have to be on the high side, making it a maximum. You'd have to write all that. Downward facing parabolas have extreme values that are a maximum, but that's sufficient. You have justified that this x value of 25 gives you a maximum point on the graph, right? If you're doing it analytically, and that would be your choice, you could either make a sign chart, which nobody likes doing, not even teachers, or you could use the second derivative test for Extrema. So second derivative test addresses concavity. So I'll take my second derivative, come up with a -2. All right. This is telling us that it's concave down for all x. All right. So if a function is concave down in its entire domain, and you have an extreme value that could either be a maximum or a minimum, it must be a maximum. All right, so that's telling us, guess I could have lived with that, but it didn't look nice. Therefore, maximum. All right, so we have an x value.
You say relative max or just maximum? So it would be right to say relative maximum?
You'd be right to say relative maximum. In this case, you could get away with saying max because it turns out that it's both the relative and absolute max in the graph. So kind of got a little cute there. So we have the x value of 25. If you go back to the relation where x plus y equals 50, we now know that the y value also has to be 25. So our final answer would be the dimensions. Oops, wrong side. So I'll just say answer 25 feet by 25 feet. What are the dimensions? Never ask for the actual largest area, so we're good there. But if you needed to figure it out, just 25 times 25 is 625 square feet, right? So, yeah, takes a little doing. I mean, it's probably, you know, relative to the amount of work that it would have taken in like in a middle school class to come up with this answer. This seems like extreme because really it's just a matter of saying, well, it's a square, and so therefore it should be 25 all around. Done. Why do I have to do calculus? Well, we've got to start somewhere. You know, just like this problem. You know, I'll do this same problem in my Algebra 1 class. Next period? Maybe tomorrow. Same problem. Even the part where we find the sum being a minimum, because it ties together with the concept of factoring. Right? So, you know, there might be some radicals in it, but conceptually it's the same idea. But we're going to apply calculus to it. So two positive numbers. You don't have to define your domain. It helps if you make a note of things to yourself. I mean, if that's the kind of thing that helps you, I guess. But if I get a negative answer, I'm going to dismiss it, obviously. Two positive numbers, no indication that they're going to be the same. So x by y is going to be equal to $1.92, and whose sum is going to be a minimum. All right. So that's telling us that we have a sum of two values. Those two values we kind of defined as x and y. I didn't explicitly state it, but you know, it's not freshman year, so you don't always have to write let x equal this, let y equals that, unless you think it, you know, it's not obvious, right? So what I will do here is define a relation s equals x plus y. In my Algebra 1 class, I take off every single time. They don't write let x equals this, and they don't like it, but at that point, their work is so disorganized and jumbled all over the place that a person reviewing their work could not make the reasonable assumption that they knew what x and y represented. So it's really more of me also testing them on whether or not they knew what x and y were. Here, if you write these two equations, you know what x and y are, right? So we kind of dial it back a little bit. So S for sum would be the sum of x and y, all right? So the relationship there would allow us to make another substitution. We'll do y equals 192 over x. So s would be equal to x plus 192 over x, which I could also write as x plus 192x to the negative first. This is the one I want to minimize. All right, so I'm looking for a relative minimum or an absolute minimum. Now, it's not a restricted domain, so if there isn't a natural absolute minimum, then it's not something I would be able to find. So s prime would be 1 minus 192 x to the negative second. Set it equal to 0. Clean it up. I'm going to multiply everything by x squared. So 0 equals x squared minus 192, which would make x squared equal 192. And so I'll say x is equal to the root of 192. All right. And actually, this is surprising, but this is a numerical representation of the physical problem in number 1, because you're talking about a product that could be thought of as an area, and a sum which could be thought of as a perimeter. So when I was saying that the maximum area is obtained by square values, well, a minimum value would also be obtained by square values. So square roots in this case, square values here, square roots to give a minimum, right? So it's basically the same idea. All right. So I need to verify that this is in fact going to be a minimum. So this is a critical value. There was a negative critical value, but they're only looking for positive numbers, so I ditched that. I didn't even consider it. Second derivative test, if applicable. I know 0 would be a bad number because of domain considerations, but 0 didn't come up as a value of x, so I'm good there. What is that, 384? X to the negative third. So if I evaluate that, it's not constant. So if I evaluate it at 192, the result is going to be positive. That's all I care about, positive versus negative. So therefore, concave up gives a relative minimum. This one I'm not so sure if it's an absolute or relative. I know it's definitely relative. I just don't know if it also would be absolute. The other one was parabola, so it had to be absolute. All right, so here we know it's going to be a relative min. So I have my x value. So therefore, we're looking at x equals 192 as a radical. But then, if I divide 192 by the square root of 192, I get the square root of 192. And that is all she wrote.